Hello, everyone. I'm Chris Musko from New York University, and it's my great pleasure this morning to introduce Marco Cuturi for our first plenary talk of the day. Marco is a machine learning researcher at Apple, and he's also affiliated professor at the Polytechnic Institute of Paris. He received his PhD in 2005 from Paris Mines, and since then has had a broad and varied career in machine learning and data science. He's spent time at Google Brain, Kyoto University, Princeton University, the Institute of Statistics and Mathematics in Tokyo, and also some time in finance. Many of you in this room know Marco from his extremely impactful work on the theory of optimal transport, and in particular on efficient computational methods for optimal transport, which we heard a bit about in John Niles-Weed's talk yesterday. Marco's work is distinguished by his elegance, and he has a number of powerful results which have really opened the door for the widespread application of optimal transport in machine learning, the natural sciences, and beyond. So I'm very excited to hear from Marco today. Without further ado, I'll turn the stage over to him, and let's give him a warm welcome round of applause.
So I really wanted to thank everyone here involved in organizing the conference. Thanks a lot for the very kind words as well. So today we'll be talking about some recent line of work that we've been pushing in recent papers. So actually, you might recognize that John Weed, yesterday's speaker, is also involved in one of those papers. And so this is, I'm going to talk about those papers mostly. I also wanted to put there in the title slide a reference to a toolbox that we are developing actively. So this is a toolbox that is developed in JAX. So JAX is this automatic differentiation framework in Python that makes, all of the computations of optimal transport quite seamless. And so I wanted to advertise this as well because I'm very actively involved in pushing those efforts. So before I actually talk about math, very short, basically, ad to say that we are currently recruiting interns. So if you're interested in working with us, so this would be in the Paris office. Please contact me or reach out to the email address there below. Anyway, please reach out. So I will start this talk with a little puzzle that will look a lot like John's puzzle yesterday, maybe a bit simpler, because it will only involve basically 2 time steps. But if you were not there yesterday, so let me just set the scene. You enter a room, the room is dark, okay? You turn on the lights, and then you see a few points in that room. So here it's pictured as 3D, of course, configuration, but we could be in very high dimensions. Doesn't really matter. And then you start looking at the particles, and all of a sudden someone turns off the lights again. And so for a few seconds, you're lost. You don't really know what's going on in the room. Thankfully, you turn on the lights again. And here you see the same particles, but you see that they have shifted in position. They are in a different configuration. The challenge here, though, is that each particle doesn't have very distinguishable, features that help you trace which particles was which particle before. And so you will have this kind of problem that arises quite often in science. And so the question is, if we are trying to reconstruct a bit what might happen, we are going to label the source distribution as red points and the target distribution as blue points. And the question that I have for you, of course, is basically who went where. And John mentioned this yesterday in his talk. This is a very ill-posed problem. There's probably, all sorts of weird explanations that you can come up with. I don't know, something like this, maybe this is what happened. Those are the really very twisted trajectories that the particles took to get where you see them, land in the target configuration. So we will probably need to add some prior knowledge to shave out, some of those weird solutions. And so one thing that we can at least start doing is just simply assume that the particles, while the light was off, they followed some straight line trajectories. So they try to do this in a fairly, energy efficient way. But even with this assumption, we of course see that there are quite a few possibilities that are left. And actually, if we have 6 particles on the left and 6 particles on the right, we basically have 6 factorial different possible assignments. And so this would make up, 720 different stories that we could select, to explain that the red particles went to the blue particles. So here comes a notion of trying to add even more prior, and the prior that I'm going to add is that of a cost function. I will try to tell you, roughly how costly it is to move from any of the input configurations, input points in the input configuration, to any of the points in the target configuration. So I will need you to supply, maybe here 6 times 6 cost values between each pair of points. And once you do that, then we're really back to something that we should all be quite familiar with, which is this, optimal assignment or optimal matching problem. And the way you would phrase this is, I want to find the permutation that, on average, incurs the smallest cost. So I'm going to basically associate to each xi a y sigma I, and here sigma, a permutation, is my variable. So thankfully, we know how to solve these problems. This has been around for at least 100 years. And Kuhn, in a paper in the 50s, actually called this, basically highlighted this problem and proposed an algorithm to solve it that is called now the Hungarian algorithm. So we find a solution for this problem, and we now have to think about, more challenging, try to open up a bit this thread and think about what could happen now that we have, input and target configurations. How can we actually generalize this out of sample? So the problem that I will mostly tackle in this talk is, given input and target configurations of points, what would be a good predictor so that if you give me a point that is not in sample, I can predict where it will go closer to this blue distribution. So this is going to be the question I'm going to ask, and this is basically known as the Monge problem. Before I actually jump into the mathematics of the problem, I would like to give a bit of motivation that we have been pushing in recent works. And the motivation here comes from single-cell genomics. So imagine you have a patient that has a tumor. You will take a biopsy of some tissue, and then you will have basically this soup, of cells. And you would like to understand what kind of treatment would actually work for that patient. So a typical approach here would be to gather data. So you would take, cells, make them, sample a few of them and make them, go through some sequencing apparatus that will give you a feature vector, typically of very high dimension, that tells you at that point in time, basically, what were the RNA strands that you could count, in the cell. So this gives you a feature representation of cells, in this tissue. One of the issues with this mechanism is that you have to kill the cells when you actually measure them. So you have to split them open, count RNA strands, and so of course this means that you cannot put the cells back in the sample. Now, we are going to apply a drug to the remaining cells, and for a few minutes, hours, we are going to let them, interact with the drug, and a bit later, we are going to sample again cells that now should be from a distribution that is representative of treated cells with that drug. And so that will give us another bunch of cells that we are going to sequence again. So we're going to have another point cloud in dimension 35,000. And here, really the goal of this field is to understand how we can abstract out some map that explains what a drug is, how a drug is acting at the level of each cell. So if I was able to tell you, that if you are in a cell in this area of the gene expression space, giving you the drug will basically either move you in this direction or this one, then I will have a huge tool, a huge predictive power to be able to basically foresee what a drug might do on your tumor or on your problem. And so this is the goal, and the goal here indeed is basically how can I recover from input and output samples a map that I might use in the future, maybe for another patient, another reading for another patient that will tell me how this particular drug will act on your cells. So this is a fairly useful tool, I think, right now in single-cell genomics, and we've been pushing this in different directions. So one is a recent primer review paper that describes a few of those methods, and another one which is a bit more large-scale and involves more advanced problems than the ones that I'm describing here, which, for instance, will also account for spatial interactions, is a paper that we're currently pushing right now and is currently in final revision. So this is for the motivation. Now back to the math. So the Monge problem. So this is a problem that was first described by a French mathematician called Monge in the 18th century. And for about 200 years, nothing much happened around the problem he had defined until we had to find some other mathematicians 200 years later that came up with some very important results. So I'm going to describe these results. But first, let me describe the problem. So the problem will sound familiar, now that we've been giving the motivations. So imagine you have an input probability distribution. Let's assume it has a density, mu. And you have a target probability distribution. This is a nu. And we are going to consider maps that push forward mu onto nu. So what do I mean by a map that does the job of pushing forward mu to nu? It's basically a map that will be here, let's say, taking a location x, a vector, as input, and outputting another vector as output, and which on aggregate will be able to push or move around the mass of the measure mu onto the measure nu. So mathematically, if you want to define this rigorously, this just means that you are going to push forward, measure mu with the action of t, and you want it to land exactly at nu, which means that if you're taking a box or say a measurable set or in the support of nu, if you're looking at the inverse image of that box, so that is you're gathering all of the points x's that land in this set B, then you have another set. And this push-forward constraint basically means that the measure of this inverse set according to the first measure mu is equal to the measure of B according to nu. So once you have this, you have, I would say, a feasible solution to the Monge problem that Monge proposed. The problem is, among all of those maps that are pushing forward the measure mu onto the measure nu, which one is that which is saving me the most energy? So you really have to look at this integral as saying, for each point x, I will move it towards t of x, and I will incur cost c of x to t of x, and I am going to average this over the input measure mu. And here, I know that at least t is doing the job. So this is maybe the favorite formulation of optimal transport for mathematicians because it's very exciting. It's it's this map formulation, but unfortunately, this is a very hard problem to solve. So one of the challenges in optimal transport, and maybe the fact that nothing happened between Monge in 1780s towards Brognier in 1980 something, means that the problem is really, really hard. So we had to come up with a different formulation of the problem to be able to solve it. And so this is where the other facets, I would say, of optimal transport pop up. Optimal transport is really a field where you have countless formulations. So this Monge formulation is maybe one of the canonical ones, but there's also the Kantorovich formulation, which is very important and directly related to this Monge formulation as a relaxation. So what does Kantorovich bring to the table? Where instead of looking for a map that will bring x to t of x, you can see this x to t of x as a conditional probability that is a Dirac mass. So you could relax this and say, actually, from x, I could go into multiple y's and not necessarily just a t of x. This means you can introduce some conditioning or even simpler, maybe a coupling between variables x and y's. And you want a coupling that has the first marginal mu and the second marginal mu. And once you relax this Monge formulation onto this coupling formulation, then you can still use the same old cost and integrate it, but now you're going to integrate it on this entire coupling. Let me say that there is another facet, in this optimal transport cube, where instead of looking at this coupling formulation, we are going to look at a dual formulation where we are going to look for test functions, f and g, that will maximize this this integral with respect to the first measure and integral with respect to the second measure. So to be simple, this is a bit of an outlier, I would say. The Monge problem is a hard problem. It's not a convex problem. But both this problem here on couplings and on the dual variables here are linear programs. So, and they are dual to each other. So they are much easier to solve. And this is what, OddJax, the toolbox that we've been pushing, is actually doing quite well. John mentioned yesterday, that we could use entropic regularized transport for this. This is one of the ways, you can speed up the computations of those problems here. Let me say that there's many more facets actually, so it's not even a cube anymore, or maybe it would be the back facets that I'm not showing there. So you probably heard about the Benhamou-Brenier formulation for optimal transport. There's also the Monge-Ampere PD, which is tightly linked with also some of the results that we'll show later. John was mentioning SDs, the Schrödinger bridges. It's endless, and then we can even go to quadratic optimal transport problems, Kolmogorov-Wasserstein, et cetera, et cetera. So that's why this field is quite exciting. It's basically looking at this notion of aligning data, but under multiple ways. So what I will present today, and this is known results, but this will serve as the foundations, for the tools that I will present, is how to go from an efficient estimation of the dual variables to something that will look like a transport map. So this is one of John's contribution was really instrumental in this direction, and we're going to use it. So rather than drop formulas from heaven and just give them to you, I would like to rederive them briefly. So bear with me for a few slides. If you're not familiar with optimal transport, this would be a bit of a fast forward, but maybe at least I will give you the idea of how we go from those dual variables to the optimal transport map. So the first thing is, let's take a look at this problem, the dual problem that I just introduced. It basically says if you are comparing two measures mu and nu, I am going to look for two test functions f and g, such that they basically maximize the integral of f against mu and the integral of g against nu. The twist here is that, of course, if this was the only requirement, then f and g could be infinite, and then I'm done. Now, of course, the problem here is that we need that f of x plus g of y is smaller at any pair xy than the cost going from x to y. So this is a very natural, this has a very natural duality interpretation in terms of prices. You can see f and g as price functions, etc. So rather than going to this interpretation, I'm going to just look at the equations, and I'm going to ask myself, okay, I have a problem, an optimization problem with two variables. Suppose I just freeze function f for a while. What happens to function g? Is there a good candidate for function g that pops up? Of course, my interest is to make g as large as possible, since I'm taking a soup of integrals. And so the only thing that I need to check is basically this constraint here. So f of x plus g of y is smaller than the cost between x and y. Okay, this means that g of y needs to be smaller than their difference. Okay, this means that in particular, if for g of y, for any x that I take, I have this inequality, I can basically summarize it, reduce it to the fact that g of y must be smaller than the infimum over all x's of c of xy minus f of x. So that sounds like the only requirement that I really need to apply to g. If g is smaller than this, then it's done. I mean, this is the best I can do. It's simple. And so this is called the C transform, or C concavity of f. So just to summarize, this looks like a problem with two variables, but in fact, if you just freeze the red variable, I can pick the best blue variable there is for that red variable. And so this is why I'm putting this, blue line on top of this red function. So this transform is going to be handy. Now, let me prove this really very important result that people call the Gangbo-McCann or Brenier theorem, which is as follows. Imagine I gave you the tools, of, the blue transform of a red function. You can imagine very quickly that this has an analogous where the red transform of a blue function, it's the same thing, but the other way around. And I'm going to use a result later on that says that, functions that are of interest for this problem are functions that are themselves, red functions that are themselves the red transform of a blue function. But this I will use later. Here is the result, that the Gangbo and McCann proved. They say, if you're able to find the best f star, that maximizes these two integrals, so I don't really need the g for now. If you're able to find the f star, this is a linear program, so this sounds, okay, doable, maybe a bit difficult, challenging, but it's a linear program. Then you get for free the Monge map. So it's quite remarkable as a result, because it says that even though we are not able to solve this non-convex problem on the right, the Monge problem, we can actually use the result of a linear program to get the optimal transport, the Monge map, for free. So the expression of this Monge map is not particularly simple. It basically involves a few gradient transformations, some inverses. So here, of course, I will do this, as a physician. In physics, it's mostly going to be a non-rigorous proof. Okay. So here, of course, this is all rigorous when you actually go to the proof. But the proof that I'm going to show is of course, very sketchy. So the way you get there is actually quite simple. It uses, basics of optimization. So the first thing is, we are going to consider a pair of points, x0, y0, that are in the optimal coupling. I didn't talk too much about the optimal coupling, but imagine, you run, Kantorovich and Kantorovich dual, you get a coupling, you get f and g. Usually, actually, they're by just duality, you can recover one from the other. And we are going to assume that, there is a pair of points in which the coupling has mass. So x0, some of the mass of x0 is transferred to some of the mass at y0. This means by KKT, or even just in linear programming duality, that the constraints are saturated for the pair of dual functions f star of x0 plus g star of y0. This is just textbook linear programming. Now, remember that I said, essentially, when you give me a red function, I can give you the best blue function there is. So I might as well just simply assume that my g star was my blue transform of the red function. So this means, in particular, if I just flip, this, it means that I found a couple of points x0 and y0 such that I have this identity. But now, you have to go back to my definition of what this thing was. The blue transform of a function f is the infimum. Here I changed the variable name to put it like a z. Is the infimum over all z's of the cost between z, y0 minus f star of z. Okay, so those are two things that I landed on, in parallel. This was the KKT condition, and this is just my definition. So what this means in particular is that this x0 here must be one of the minimizers of this thing here. So this means that if it is a minimizer, the gradient of this quantity with respect to the first variable at x0, y0 minus the gradient of f star at x0 must be equal to 0, and therefore I have this equality between them. And now, if I assume, and this is, something we'll assume in the talk, that this map here is invertible, then you can just say that there is only one y0 for which x0 transfers in mass 2, and that y0 is given to you by this formula. Okay? So it's a sequence of assumptions that make this formula hold. And it's going to be very useful because here, of course, taking the inverse map of this gradient 1, first variable, etc., might seem a bit complicated. But if you start making a few simplifications, so for instance, one of them is something we used a lot in transport, is let's assume that our cost is translation invariant. So it's a function h evaluated at x minus y, and I am going to assume that h is convex, if not even just strongly convex. So then, in that case, if you just write a sequence of simple equalities, you realize that my operator here is just simply x minus the gradient of h inverse applied to a point. And that's because of duality here as well. Sorry, because of convex conjugacy, the gradient of h inverse is just simply the gradient of the Legendre transform of h. So this operator is more or less given to me for free. Of course, we could study more complicated cases, more complex operators, but today we're going to mostly stick to this. So to summarize, this is known. translation invariant cost, you have basically a better, nicer formula, which is still going to involve grad f star, but this is a different star though. This is grad h star, the convex conjugate of h, and this. And then if you actually use squared Euclidean cost, okay, the default choice, then of course the gradient of h is equal to gradient of h star is equal to identity. And therefore you have this formula here, which says that the optimal transport is just x minus grad f star of x. So I want to point out something because, of course, there might be some confusion here. None of those f stars are the same, right? Every time I change the cost function, I get a different f star. So f star is implicitly parameterized by the cost function. But if you give me a cost function, I'm able to run a solver to approximate f star, and I can plug it in this formula. Just one very quick side comment. This, of course, is the gradient of this here difference. And you can prove, basically, when the cost is squared Euclidean, that this is convex. And so this gives you one of the famous instantiations of this Gangbo-Macan theorem, which is that the optimal transport between two measures. So here I want to take back that sentence, maybe the L2 square, the squared Euclidean distance optimal transport, is going to be a gradient of a convex potential. So the way you get that convex potential is slightly different from the dual potentials. It's some slightly different reparameterization, but it's roughly the same thing. Instead of having this f and g, here we will have a problem that will involve phi, a convex function, and its conjugate. So today I will be talking very briefly about this, because this is more past contributions, and I will go towards 2, which is basically go up a bit in this ladder, where I am going to explore a bit more how exciting it is to look at those h functions that are not necessarily just square Euclidean distance. And if you remember my title, I'm going to focus on elastic cost. So just very briefly, one of the things that was proposed to handle this problem is, okay, let's just simplify the problem a little bit, do some dimensionality reduction, bring all those points to a smaller dimensional subspace. I still want to look for an optimal transport that is able to predict where treated cell will go. So I will just try to look for something that looks like this Monge problem. And instead of using this Monge problem, we'll use this trick of reparameterizing everything as a gradient of a convex function. So here I will try to look for a convex potential that is minimizing this objective. And this objective is not so easy to minimize because essentially we have a convex conjugate here, which messes things up a bit. But this was proposed in recent years. And the family of convex functions that people use to optimize this are called ICNNs, or input convex neural networks. And so I will very briefly describe them if you've never seen what a convex neural network looks like. It's essentially some kind of recurrent neural network where you actually feed again and again the same vector x to some to every layer, and you're composing things so that you stay convex in the input variable x. So it has an hidden state. The hidden state is essentially a collection of convex functions, and you keep on updating them and according to some parameters that you define. And if in this recursion here, you have a certain constraint on the parameters and a certain constraint on the activation functions, then everything stays convex in the end when you collapse all of those values to a single real number. So I will go very fast on this. This kind of works. It works okay. It's hard to train. For me, I always have trouble training this because essentially this conjugate here, which is typically handled by having a surrogate function that should look like the conjugate of f star. So what I will present now is a bit simpler conceptually, I think, and doesn't use for now neural networks. And it is the following. Basically, I am going to play with cost functions h that have a certain structure. I will look for estimators of these dual potentials and plug them into this formula and see a bit what happens with those optimal transport maps. So, of course, if I want to plug f star into this formula, I still have the same problem, which is basically how do I estimate f star. And so here, the main tool that we're going to use is basically inspired by John and Aram's result on the entropic map estimator. So here is the roadmap. So I want to somewhat be able to evaluate this. I will look for a good approximation of f star. And the way I will get this is using samples from both measures by running a synchron solver, which here I'm not going to describe what it does, but essentially what it gives you is a good pointwise approximation of what the optimal dual potentials would look like on any of those points xi's and yj's. And then I am going to recycle those pointwise estimates into a formula that is really what John and Aram proposed, which is a log sum x type of potential. So what this says is, if you want to have an approximation of the potential f star at xi, then you can just directly go to the point, to the value f star I. But if you want to compute it out of sample, John and Aram showed that this, is a good approach, and it's motivated by some kind of soft C transform that I showed earlier. So we have something like this. So I'm going to call it f hat n. It's something that uses data and uses values that were tuned previously with a synchron algorithm to come up with an estimator. Now, if I want to compute the gradient of the f star, a nice feature of this is that actually you will see very clearly, if you have a log sum x, the gradient will naturally be some kind of expectation of a Gibbs distribution. And so it turns out that this gradient of f hat n evaluated at x is just a convex combination, so it's convex weights that depend on x, of some gradient of h evaluated at x minus yj. And the interesting thing for those of you who like Bregman divergences is that if now I start looking at grad h star of this, then this is actually called the Bregman barycenter, because it's grad h star applied to a convex combination of grad h of some points. So that was a interesting observation. And now comes the, I would say the meaty part, the most interesting part, which is how do we set those h stars if you want to get something interesting in return? And so it turns out that if you set h to be an elastic cost, so a squared Euclidean norm plus any regularizer tau of your liking, then grad of h star is equal to a proximal operator of tau. So this means that if you actually follow my roadmap, the transport for any point x is going to be equal to x minus a proximal operator applied on some vector, which is the vector that is the gradient of the potential that is optimal for that cost. So there is a bit of, things are, we really have to keep in mind that this f star or f hat depends on the cost itself. So here there is an opportunity. I'm basically telling you that whenever I'm going to run an optimal transport pipeline, T of x minus x, which was people called the displacement, is essentially going to be a proximal operator applied to some vector. So this gives me a lot of leeway to impose structure on the optimal transport that I want. And here, probably there's something I should have said earlier and emphasized earlier, but I didn't. When people tell you about the optimal transport between two measures, you should really hear this as the optimal transport for a certain cost. And that cost is 99% of the time the squared Euclidean distance. So here we're trying to change a bit this and say, no, actually, there are as many optimal transports as there are costs out there, even if you give me the same two measures. And so by changing this very important parameter of the cost structure, we're also changing what would look like a plausible transport between the two point clouds. So let me just show you some very basic examples that we can run on with odd jacks. So imagine my cost is, again, the squared Euclidean distance. So this is the classic thing. If I give our solvers those 2-point clouds and I try to estimate the map that I just showed on out of sample points, this is roughly what happens. Okay? Sounds okay. It basically tells me that if I have points that are in sample, they will basically move around towards the target measure. Now, if you start changing the cost with our new approach, then if I add some L1 regularization, remember this is going to basically enforce a transport that will look like T of x minus proximal operator. So here it will be soft thresholding of some vector. And so as a result, of course, the transports that are outputted here start to have this, inherit the structure of the proximal operator, so they're sparse. So they will have only one out of two, let's say, variables that are turned on. And we can start playing with all of you. We can recycle basically all of your proximal operators that were encoding some meaningful structure in let's say, variables as regularizers, here to encode some structure in displacements. So here, this is an example with the K-overlap norm, which is trying to mimic a bit the L1 norm with better properties. And so here we see that the more we regularize, basically, the more sparse, basically, the transport will become. So here, maybe just to go back to motivation, why do we want this? Why is this useful? Well, one of the reasons this might be useful is that transport is really plagued by the curse of dimensionality. So it's very hard to do transport in very high dimensions. And that's why, even in the input convex neural networks examples that I gave earlier, we usually do dimensionality reduction to a smaller set of features. So what we are trying to do is essentially say, I would like to estimate transport that explains what happens between, blue and yellow here. But somewhat, I would like to constrain the space of what's possible. And I would like to do this in an elegant way, I would say. I don't want to go too much into the details of, basically imposing a structure on the Monge map, because that would be very hard. Instead, what I want is basically to promote transports, in this case, for a sparsity regularizer, that would basically mostly happen in 1 out of 3 dimensions. And what is going to be a very big difference, I think, with this classic sparsity literature, is that here the sparsity is different. The sparsity pattern will be different depending on the starting point. So when you use the lasso, typically, we'll be thinking about a certain beta regressor that has a certain sparsity pattern. It's basically, this is what you're going to look for. Here in transport with these norms, we are looking for a different sparsity pattern at every point. So this is the goal. So let me just say that this is actually done in a way. There's lots of questions on, how to set the hyperparameters, the regularization strength, as you can imagine. But it's quite easy to play with this model in a few lines of code. So here I'm just showing a few examples. Here, let's say I'm using, this is John and Aram's entropic map estimator. What happens is if I use a different cost function, then immediately you see, these patterns that arise. I will be a bit brief also on the experiments. Essentially, what we see is that we have no degradation in predictive power, but we can get to that predictive power when we're going to make predictions, in cell space, using far less variables. So our transport is modeling far less changes, which, even in this genomics setup makes sense, because you would hope that, a treatment is not going to mess up, let's say, 30,000 out of 35,000 of the genes, but maybe just target 100 of them. So that's what we're trying to do. So in the next minutes, what I want to just show is some recent progress on this approach. So after proposing this, going one level up the ladder with more complicated costs, the question we ask ourselves is, okay, it's cool to play with those different structured costs, but one of the things that we are really missing from this good old squared Euclidean distance setup is that we do not have access to ground truth optimal transports. So let me explain a bit what I mean by this. So you remember that Brognier basically gave us this big result, says that whenever you have a convex potential, if you compute its gradient, it's always going to be an optimal transport from wherever you start to wherever you land. So it's a very simple recipe to compute, to propose benchmarks, for instance. You just take a bunch of points, apply to them a gradient of any convex function of your liking, you get another bunch of points, and now you have a ground truth optimal transport. This is the best way you can go from the source to the target. So we don't have this for H. At least we didn't know how to do this for H, more structured H functions. The other question that we asked ourselves in that NeurIPS paper is, okay, it feels like we're opening a bit Pandora's box, because of course, some people might come to you with a very specific prior, I have my H or my tau that I like for my application, it's going to work, and then we can provide them with this algorithm. But in general, you always have access to a family of regularizers, not really just one, that you like. And so the question we ask ourselves is there a way to tune adaptively the parameters of that regularizer? So let me explain very quickly. Actually, it turns out that the first problem of computing ground truth optimal transports for those exotic costs is actually not that hard. It's just following the playbook, of this optimal transport theory. It just says that if you give me a function, a potential function g, and I compute its H transform, remember this operation that I could do when I was proving duality, then if you can actually evaluate this function here, this g bar h, or I used to call it the blue transform, or the red transform, sorry, then if you're able to do this, you can get for free basically a transport that will be by definition optimal for this cost function h. So in order to be able to minimize this exactly, for now, of course, the obvious requirement would be that g is concave. And so this is what we've been playing with for now. We might be playing with something a bit more, multimodal, I would say, multiple modes in G, and that should also work. And so if you are able to do that, you can generate ground truth optimal transport maps. And how can you minimize this? Well, actually, it's not so difficult. You can just use proximal gradient descent. Because if G is concave, then you should get where you want. So this means that, for instance, I can give you examples, of course, of this H transform. Imagine my base function is this concave potential here, and I play with different H functions with different regularizers. I will get different H transforms. And this helps me, in turn, create synthetic optimal transport examples where I can tell you now that, let's say, this map here is an optimal transport for the elastic net, let's say, cost. So going from those blue points to those orange points. And here you can see there is a bit of a degeneracy, of course, because some points are even in place. So we can start studying what it means for optimal transport to be optimal with respect to this cost. And so we've been playing with other cost functions. So one of the cost functions that we've been playing also is a subspace regularization, where we are going to essentially promote that the displacement happens in the subspace generated by B by simply penalizing the norm in the orthogonal of B, the orthogonal projection of X onto the orthogonal of B. So those are, as you can expect, if I increase the regularization term, I will start having transports that are more and more aligned with this direction. So again, this is not transport happening in a subspace. This is transport happening in a full space, but where the displacement is actually in a subspace. So now that we have this ground truth, generator, we can at least go back to the previous work that we had and say, okay, was this method, using this the approach of John and Aram generalized to other costs sensible? Does it work? And actually, we have a lot of experiments that do show that this seems to be working. The other part, and I'm going to be a bit faster here because I'm running out of time, is about learning the parameters of such regularizers. So here we just did something quite simple for now. We try to look for a regularizer that is, again, this idea of penalizing anything that happens outside of a subspace, and hence penalizing the orthogonal projection of Z onto the subspace of A. Here. So this is basically saying I want most of the transport to happen in a subspace generated by the columns of A. And so to optimize this, we came up with a loss that is a bi-level optimization problem. And so whenever you say bi-level optimization, it means that we will need to differentiate through the action of actually getting optimal transport couplings. I won't get too much into the details, but I was very happy to see yesterday that there was a poster that was actually looking exactly at this, how to provide numerically stable ways to do implicit differentiation of optimal transport coupling. So I will be a bit brief on this. This seems to be working at the moment, so if you're interested, please look at our NeurIPS paper. In particular, we're able, in synthetic tasks, to recover very well the subspace. If the ground truth optimal transport is really happening in a subspace, then we're able to recover it very well. And we also observe in single-cell genomics data that this is actually helping the estimation. So in a way, coaxing your transport maps to move mostly in subspaces. So it would be, if you want some kind of PCA argument for optimal transport maps, seems to be cutting some noise and also give better prediction power. So with this, I will conclude. So I think optimal transport, really, I was talking about this cube. It's a set of tools that have a lot of flexibility. And John was also mentioning yesterday, some computational challenges. So there's a lot of flexibility to provide modeling tools, priors. It's not always easy to get, the tools to work with that flexibility, but this is why I think it's very important to, push at the same time those frameworks that are able to very quickly test, those new ideas. And so this is why I really encourage you, if you're interested in these areas, to look at the toolbox. And I also want to say that I have other students and interns that have been working on very exciting topics related to optimal transport, in particular those two posters, so two posters at Europe's this year, and actually John is also in this one, and another that is more related to flow matching. Thank you very much for your attention.
Great, thank you so much, Marco. If people have questions, you can come up to the microphones on either side.
Hi, thank you for a great talk. So I just have a question about the slide you went over a little quickly about learning transport map in the subspace of A in low dimension.
Okay.
Oh, just wondering if it has any relation with the latent optimal transport.
So what do you mean exactly by latent optimal transport? It would be like optimal transport in latent space?
With the cost, with the transport map of the form Q diagonal 1 over R and then R, H, sorry.
Can you repeat, sorry?
That the transport map is in the form of two matrices, like a tall and skinny matrices.
Okay. I think I know what you mean. So here you're talking about coupling solvers, and you're trying to think about a factorization of this matrix P star, right? That would be, let's say, a thin matrix times another thin matrix. Is that correct?
Yeah, in one of your paper, that
Yes.
the transport map is already solved in that form.
Yeah. So I think those are a bit too different, related but different views. So what you're describing is basically how to, so this is a bit the game, with this cube in transport. There's so many facets that, sorry, let me just skip those animations. So usually when we try to get solvers for this facet, it's useful to add some kind of, as you say, low rank or factorized or latent. There's been some very interesting works recently on this as well, that helps you. Here I would say it's this other side of the cube. You're in the yellow cube where it's more like transport. And so I don't think there is an immediate relationship between the two. It's, there might be one, but it's not clear to me.
All right, thank you.
Thank you.
Yeah, thanks for the great talk. I have one question about the curse of dimensionality.
Yes.
So when you limit the effective directions of the transport map to a low dimensional space,
Yes.
but everything still happens in the high dimensional space,
Yes.
are there any results or any effective algorithms that can help, that this could be useful to mitigate the curse of dimensionality? So in other words, that you can basically compute the transport map at the cost that depends more on the lower dimensional space?
Yeah, so it's a very good question. So we try to approach a bit this problem in the paper. It turns out that when you actually project everything to a lower dimensional subspace, then you have less of a statistical cost. It's better. And this goes back a bit to John and Aram's original work. But this is not really what we're trying to do, in the sense that, as you mentioned, we are trying only to focus on transports that are low dimensional, or displacements, I should be more specific. Displacements that are low dimensional, despite the fact that the points are in the high dimensions. And in that case, we don't really have a result yet.
Okay, cool. Thanks.
Yeah, thanks for the great talk. So I think I finally understand the purpose of these elastic costs. So you regularize the cost to encourage the transport to be constrained. I guess another approach I've seen in the literature is instead of adding entropic regularizer to the Cantor-Rovich form over here, you add some other strongly convex regularizer.
Can you talk louder? Because
Yeah, sorry. Is this better?
Yes.
Okay. I guess another approach I've seen is instead of adding entropy as a regularizer to the Cantor-Rovich form, you add like a square or something strongly convex. And people claim this can give you like a sparse coupling or something like that. Do you think the elastic map is better?
I disagree a bit with this. Again, this is a bit this game of which facet you're playing on. If you start regularizing the coupling matrix, you will get, associations between the xi's and yj's that will be have different regularization, as you mentioned. If it's an L square regularizer on this coupling problem, then you will then get different set of points that you will map to, maybe sparser. But then you still need to make the step of falling from this coupling facet to the T.
Yes.
And so the question is, a very canonical way to do this is using something called the barycentric projection. So you're basically saying, okay, if I is connected to J1, J2, J3, I am going to average J1, J2, J3. And then you have some form of map, right? But this is basically this vector here that we're trying to give some regularity to. And even, I would even say, beyond that, out of sample.
Yeah. Okay, yeah, so regularizing the cost is better.
Yeah, I think it's two different, again, it's playing on two different parts of the same game. So it's fascinating. It's not clear to me how you can go from one to the other. But it's for now, at least the way I see it is you're adding regularity on the Monge map. So this is a vector-to-vector function. Or you're adding regularity on the coupling matrix, which is n times m. See, it's two different dimensions in a way.
Yeah. Thanks.
Okay, I don't want to eat too much into the lunchtime, so let's actually take the rest of the questions offline and give Marco another thank you.
Okay.